Hello and welcome back to the lecture of time series econometrics. In this lecture, we are going to cover a very important topic called characteristics polynomial for AR and MA series. So we're going to see what is that characteristics polynomial and what is that characteristics equation that we're going to derive. And basically three things we'll address. One is that how we can get the characteristics polynomial. Second, why these characteristics polynomials are so important for us. And third, what are the assumptions behind this characteristics polynomial when we actually derive that. So to do that, let's first actually write down a higher order AR. So minimum higher order AR series that we can write is AR2. Basically, if I want to go beyond the AR1 series. So AR2 series, so let me just write down. This is my AR2 series. So I normally write AR2 is equal to YT is equal to phi1 YT minus 1 plus phi2 YT minus 2 plus my innovation term or error term, which is IID. Now, I know the use of lag operator, and that is going to be important when we actually get this characteristics polynomial. So what I can write here is phi1 L YT phi2 L square YT and my epsilon t. Now I will take all the YT terms on the left hand side. So I can write YT minus phi1 L YT minus phi2 L square YT is equal to my epsilon term. Now I know that L behaves like a polynomial, so I can basically, it has all these mathematical properties, and using that what I can do is I can actually take YT out, and I can write YT into 1 minus phi1 L phi2 L square is equal to my epsilon t. All right. Now what I want to actually do here is that this product that I have just written down, the product form. So this particular equation, this particular form, I want to actually get specific root for this equation, okay? And we're just going to see that. So before I actually go there, so in this equation, so if my YT has to be stationary, so what I will want is this term should equate to 0, because my epsilon t is almost, basically the mean value is 0, and if I can get this term equal to 0, so that means my, now YT can have different values, so then this product, this expression in the bracket, that should be equal to 0. So I can write 1 minus phi 1 L minus phi 2 L square is equal to 0. All right. Now, I cannot really use L here as a variable because L is an operator here, right? So what I will do is I am actually going to replace L with a variable, say X, okay? So I will write, so here this is a bit tricky. Here we have to assume that as if the variable X is containing all the properties of L, and still it is behaving as a variable, right? Because only if it is a variable I can take a root. I can't take a root for operator. So it won't make a lot of sense. So what I do is, let's say I write it as X, and then I write phi 2 X square is equal to 0. So this part, this equation is known as, or this part is actually known as the characteristics polynomial. This is known as the AR characteristics polynomial because I'm doing for AR series. Polynomial. And when I compare the whole equation, when I equate this AR characteristics polynomial with 0, I call it, this one I call as AR characteristics equation. So essentially, two things you have to remember here. The innovation that I brought, one is that I have actually replaced L with X, whereas my X is a variable and L was my operator. And second, I have equated it with 0 because then only if I write it equation 1 and equation 2, so my equation 1 will hold true. Okay. So these are the two assumptions. These are the two thought behind getting this AR characteristics polynomial.